Hello everyone. My name is Omkar Desai, and today I'm excited to talk about our work Seneca. To kind of give an inspiration for the name Seneca, Seneca is inspired by the quote, "Luck is what happens when preparation meets opportunity," and it's a quote widely attributed to the Roman philosopher Seneca, and that's what our work is based on. Multimedia model training trains large models using multimedia data sets, and this process can be typically divided into two parts. The first one is where we fetch data from storage and pre-process it before loading it onto the GPU for training. This process is known as the data storage and ingestion pipeline. The second part of the process is where we actually update the weights and biases of the model using the process known as what we call training. So naturally, we can see that the training process heavily depends on the DSI pipeline to provide data fast enough for training, and this actually poses a hardware challenge. We actually compare the peak performance of GPUs and CPUs over the past several years, and it's not a surprise, but we see that CPU performance has scaled significantly slower as compared to GPU performance, and this creates a widening gap between the CPU and the GPU performance. We further measure this in practice and see that measure actually training and pre-processing performance exclusively across different hardware platforms, and see that pre-processing throughput is significantly slower as compared to the actual training throughput when all the data is pre-processed and ready to train. This motivates the need for optimizing the DSI pipeline, and which is kind of the major motivation for this work. Optimizing DSI pipeline faces several challenges, and we'll go through each one of them now. The first one is pre-processing data is computationally expensive and requires a large CPU overhead. The second challenge is that as data sets get bigger and bigger in size, they don't fit into the DRAM, and this creates storage as a bottleneck. And then finally, random data sampling, which is actually important for accurately training large models, is actually ill-suited for traditional caching policies such as LRU, and they typically cause cache thrashing. Let's now first discuss the first challenge. Which form of data to cache in the DRAM shows different trade-offs in terms of memory overhead, CPU overhead, and its reusability. First, we could cache data in the encoded form, the raw image. This requires a low memory overhead, but requires a large amount of pre-processing overhead in terms of CPU. The next option is that we could cache data in the decoded form, and this presents a significantly larger memory overhead, although it has a lower CPU overhead. And finally, we could also cache data in the final augmented form after all of the processing is done, and this presents a significantly lower CPU overhead, but the disadvantage is that we cannot reuse it over and over again across epochs. We actually measure how this trade-off impacts training by using a 450 gigabyte of DRAM along with A100 GPUs, and cache data in one of the two extremes, either completely in the encoded form or completely in the augmented form. We observe that when we have enough DRAM, caching data in the augmented form is actually faster and is beneficial. Now, this happens mainly because the breakdown shows us that the pre-processing overhead when we have enough DRAM is 70% lower, although we incur a 35% larger fetch time on average. So this trade-off shows that in cases where we have a large amount of DRAM, it's better to cache data in the augmented form. However, if we change the amount of DRAM available to 250 gigabytes now, the scenario changes significantly. Now, in this case, we observe that caching data in the encoded form is actually faster. And when we see the breakdown, we see that it has a 53% smaller fetch time, although just at a larger 13% pre-processing time on average. So this kind of motivates the pre-processing, the need for looking at the pre-processing trade-offs. The second challenge is how larger data sets make storage a bottleneck. we measured the training throughput for training ResNet 50 on PyTorch and NVIDIA's DALI dataloader on a system with 512 gigabytes of DRAM and A100 GPUs. We see that traditional dataloaders degrade significantly in performance as the dataset gets larger than the DRAM. And in case of PyTorch, we see that there's a 67.3% degradation in throughput as dataset gets larger and larger. Now the third challenge is that random data sampling, which is actually important for training models accurately, is ill-suited for traditional caching policies such as LRU, and it causes cache thrashing. We don't discuss that in a lot more detail in the interest of time. The objective of our work is to answer these two questions. The first question is how to determine the best way to utilize DRAM cache. We solve this problem by model-driven partitioning, which is based on the DSI pipeline performance model, which I'll talk about. The second question is how to improve cache hit ratio when accesses are random. We answer this by opportunistic data sampling, which improves the hit rate while ensuring randomness in sampling. Now I'll talk about the DSI pipeline performance model. Now in this case, we see that data can be in either decoded, augmented, or encoded form, and it takes different paths to the GPU. And we model the performance for every scenario here. The figure shown here is a simplification of a typical training system with DRAM, CPU, GPUs, etc. This is sufficient for explaining our model at this time and extends to distributed training easily. The performance of hardware components in this case, such as the DRAM, the storage, and the different interconnects, is actually gotten from data sheets, whereas the specific performances of the throughput of training the model as well as the pre-processing throughput is measured using DS Analyzer, an open source tool. Now, in the first case, when data is actually cached in the augmented form, all we have to do is fetch data from the DRAM, load it into the CPU for training, and that's it. The second case, where data is actually in the decoded form, we have to move the data from the DRAM into the CPU for augmentation and then into the GPU for training. The next scenario, where data is cached in the encoded form, we kind of follow the same path where we move data from the DRAM into the CPU. Here we do the decoding and augmentation processes and then load the data into the GPU for training. Finally, when data is not cached in the DRAM at all, we have to fetch data from storage, pre-process it in the CPU, and then load it onto the GPU for training. Now, the overall DSI pipeline performance is given by the sum of the throughputs of these individual pieces and by the proportion of the amount of data that is stored in each of these forms. For more detailed modeling and equations, please refer to our paper. Next, I'll talk about how we validated the DSI pipeline performance model and show its accuracy. So we validated our DSI performance model on a single node and distributed nodes. The x-axis shows the dataset size and the y-axis shows the throughput. The maximum DRAM that is used for caching in this case is 64 gigabytes, and the lines that we see here are the model performance. In this case, the red line shows when the entire memory is allocated for augmented data. The green line shows when the entire memory is allocated for decoded data, and the blue line shows when the entire memory is allocated to the raw data or the encoded data. The points on the plots show the actual measured performance, and we see that there's a high correlation between the model and the measured performance at all times. Similarly, for distributed model training, we have a similar setup. In this case, however, what we do is we split the memory 50-50 across two different cache forms and see that our model performance is close to the actual measured performance. Across all of our validations that we do, the correlation coefficient never drops below 0.9. For more validation results, please refer to our paper. Now, I'll talk about Seneca, which essentially combines MDP, which is model-driven partitioning, and ODS, which is opportunistic data sampling. First, MDP is the process which determines the cache partition at the beginning of the training job, and ODS is the process which replaces cache misses with hits while ensuring random data sampling. In the interest of time, we skip ODS and move on to the evaluation now. So the evaluation setup consists of 5 different data loaders. 2 of them are popular open source data loaders, which is PyTorch, which we all know about, and then NVIDIA's DALI data loader, which is an open source library that pipelines and offloads pre-processing tasks to the GPU. The next one that we evaluate is Shade. Shade actually caches and uses samples with higher importance. The next one is Minayo, which was originally built on top of NVIDIA's DALI data loader, and it has caching optimizations, which essentially says that we don't evict data samples from the cache. And the last one is Quiver, which samples significantly larger amounts of data samples than what is required for a batch and returns what comes out the fastest. Our evaluation is actually run across RTX 5000 GPUs, V100 GPUs, and A100 GPUs. In the evaluation, we answer the following questions here. The first one is to answer the most important question, which is, does MDP and ODS, do these optimizations actually negatively impact model accuracy? The second one is, does Seneca actually scale with newer hardware, and is it better performing for newer hardware platforms? The third one is, can Seneca handle concurrent jobs well? This scenario is pretty common in multimedia model training, where multiple DNNs may be trained using the same data set and on the same cluster. And finally, how does Seneca deliver high performance with all of these optimizations? What is actually happening in the background? The first one that we look at is model convergence. We evaluate the accuracy of Seneca with DALI and PyTorch, and we see that Seneca actually achieves the same level of accuracy as compared to DALI and PyTorch, but does so faster. In this case, for ResNet 18, we see that Seneca is 49.2% faster as compared to the next best data loader. And as compared to VGG 19, we see that Seneca is 49.16% faster as compared to the next best data loader. For additional experiments, you can obviously refer to our paper. The next evaluation setup that we look at is, how does Seneca actually perform with newer and newer hardwares? We do this to answer the question that can users benefit from Seneca more when, as the CPU and the GPU gap we spoke about keeps expanding? First, we know that Seneca is faster than prior works on the V100 GPU. It is faster than Quiver, which is the next best performing data loader. Furthermore, we also see that Seneca maintains the lead even on newer GPUs and actually performs better as GPUs improve in performance. This is because Seneca actually improves the DSI pipeline performance and pushes more data into the GPU. This is beneficial for newer GPUs. Now, Seneca training on the VGG model actually performed more than 2 times faster as compared to the V100 GPUs. And this shows that Seneca scales well with hardware. The next set of evaluations we show is to show that how Seneca performs across concurrent training jobs, which is pretty common in multimedia model training. We train across 1, 2, and 4 jobs, and first, we see that PyTorch degrades in performance with concurrency, as it does not have a shared cache and cannot benefit from pre-processing done by other jobs that are also running on the same system. Similarly, for data loaders which don't actually share their cache or have these shared optimizations, we see a similar trend where performance actually degrades with more jobs. Next, Quiver improves the DSI pipeline improves performance of training as we go from 1 to 2 jobs, thanks to its 10x larger sampling size. But as we move from 2 to 4 jobs, the training throughput actually reduced, mainly because the CPU became a bottleneck when the larger 10x sampling needed more CPU power. Now, lastly, we see that Seneca improves performance because of shared cache and opportunistic data sampling. Finally, let's look at why Seneca performs better by looking at the cache hit ratio of these different data loaders. First, we look at min-IO. Interestingly, min-IO's performance is bounded by the DRAM capacity. If we look at all of these bars, we see that the cache hit rate is approximately equal to the amount of data set, the percentage of the data set that is actually cached in memory. This is because min-IO never really evicts anything and the cache hit rate remains stable. The second one, which is Seneca, thanks to its opportunistic data sampling, we see that a 54% cache hit ratio is achieved even with only 20% of the DRAM, even when only 20% of the DRAM is cached. This is thanks to the greedy sampling or the greedy sampling that Seneca does to improve the cache hit rate of whatever is in the cache right now. Lastly, Shade performs the best in terms of cache hit rate, mainly because of its optimizations that that sample more and more important data, but overall it suffers in performance. Finally, Quiver's cache hit rate is comparable to Seneca, but again, as we saw earlier, it is slower because of a higher CPU overhead of sampling. In conclusion, we address two challenges in this work. The first one is which form of data to cache, and the second one is how to make sampling of random data samples cache friendly. We have two contributions in this work. The first one is model-driven partitioning based on the DSI pipeline performance model that we spoke about, and opportunistic data sampling, which improves the cache hit rate while maintaining randomness. We have three key results here. The first one is that we reduce training time by 49.2%, increase the DSI throughput by up to 3.5 times, and finally achieve a 54% cache hit rate with only 20% of the dataset in cache. For more results, please refer to our paper. Thank you.